But today we're going to talk about gases. First thing you'll notice is the slide format is not one that's derived from the publishers. I got this one. I inherited this one from my predecessor, our chemistry professor before he passed. Gave me all of his slides, in fact, and I like this one so much I kept it. So we're going to talk about gases. Why should chemists be concerned with the gases? Well, there's a historical component. Gases were very well known. They were understood by alchemists through the Middle Ages. And then what we would consider modern chemists, or as they call themselves then, natural philosophers. But they understood how gases behaved and how to handle gases. So our chemistry, modern chemistry starts with gases. And we're gonna cover the gas laws, which came out of the early 17th century and thereafter. What do we mean by gases? Well, we have to treat gases. One thing that was recognized by through the Middle Ages was that in certain respects, gases all behaved alike. Now, that's not chemically speaking, but physically speaking, they all behaved alike. In other words, if you had a confined gas in a volume and it was under a certain pressure and temperature, then it was going to behave if you did anything to it, like compressed it or heated it up or cooled it down. It was going to behave pretty much physically like any other gas, which was an advantage. Because if you can do that, I mean, I could just take a sample of air and do all kinds of physical experiments with them. That's when you enter the realm of chemistry that things start to diverge. But we treat gases as, we say, semi-independent particles. The ideal gas behaves as if all the particles are independent. They behave, think of them as billiard balls, right? They're moving around and they might smack into each other, but there's no interaction except to transfer momentum and bounce off of each other. But we say semi-independent because we know for a fact that they do interact to a limited extent. They're rapidly moving. They could be atoms, they could be molecules. And what's the difference? Well, atoms are representative of individual elements. Molecules are combinations of two or more different elements that behave as a single unit. So for instance, oxygen gas is two atoms of oxygen, nitrogen gas, two atoms of nitrogen. Those are molecules. But they're moving really fast. And toward the end of this chapter, this presentation, we're going to calculate just how fast they are moving. Gases are all miscible. What do we mean by miscible? That is, they mix perfectly. They make homogeneous mixtures. All gases, doesn't matter what the gas is. Put two gases together, you always get a solution. No matter how many you put together, as long as they don't chemically react. If they chemically react, then you could get something else. They do have mass. All the gases have mass, and we can measure that mass. Compared to liquids and solids, it takes a larger volume to get a measurable amount, but you can still measure a mass. So gases, each particle has mass, and since it's moving, like we said earlier, very fast, each particle has kinetic energy. Right? And you can calculate, oh, that's not very good. You can calculate the kinetic energy of individual particles using that formula. All you need is to know how much mass and how fast is it going. And you can calculate its kinetic energy. Now, the energy is going to have units. If we use international system units, this is going to be in joules. The mass is going to be in kilograms, and the velocity is going to be in meters per second. Right? So 1 joule is a kilogram meter squared per second squared. if we need to do unit conversions, that's what you need to know. What is it equivalent to? One of these is equal to one of those in these units. But they have kinetic energy. So if you're out trying to pump gas a couple of days ago, I guess it was Sunday, and you're trying to stand there and you're holding on to something because the wind's gusting up to 40 miles an hour, then you know that gases have mass and they have energy because they're transferring some of that energy to you and trying to knock you off your feet. Now, I've never been out in a hurricane. I've been on the edge of one, but not in the middle of one. And I can't imagine what that would be like. 80, 90, 100, 120 mile an hour winds. I think I'd have trouble standing up. I just might as well spread my wings and go with it. Gases, these particles are in random motion. Now, we say random motion because for a practical reason, because we don't have the computing power, we don't have the detecting power to monitor every gas molecule or atom and plot its trajectory. If we could, theoretically, we could predict what it's going to do, when and where and how. If we knew the energy, the direction, the velocity of every particle, then we could theoretically compute what would happen with the gas over the next day, year, month. But we can't do that. We don't have that power. So we treat gases statistically, and that means random. We let the molecules behave random motion, and then we treat them from the standpoint of probability. All right. We're going to look at the different gas laws. Right, and this is where we started. Study of gases is a perfect example of the progression from laws to theories. Laws just say what happens. If these are the conditions, this is the outcome every time. That's all that a law says. Theory takes those laws, and especially for gases, we find that the theory was developed to explain all the laws that had accumulated at the time the theory was developed. We're going to describe an ideal gas. There's a little bit more to it than just independent billiard balls. We're going to learn how to solve problems with these gas laws. Right. And then, for example, the Earth's atmosphere is a mixture of gases. 79% nitrogen, 21% oxygen, a little less than 1% argon, and then minor components of the others. Carbon dioxide, methane, not a whole lot of helium. It's too light. Helium just kind of goes out into space. And then certain pollutant gases. And then you have particulates that are not included in this assessment. But the gases, the air we breathe is necessary for life. For heterotrophs like us, where we have to consume energy-based compounds and break them down and derive energy from them, we need oxygen to do that efficiently. Right? It can be done without oxygen, but it's not very efficient. Some microbes do it as a matter of course, and we use them to make bread. We use them to make booze, beer and booze. But the more efficient breakdown needs oxygen. Now, for autotrophs, oxygen is a product of their activities. Like green plants will take in carbon dioxide and water from the air and use energy from the sun to store that energy in molecules that are constructed using carbon dioxide and water. So we kind of feed each other. They feed us oxygen and we feed them carbon dioxide waste. So for plants, carbon dioxide is food, right? For the EPA, carbon dioxide is a pollutant. And that's a whole other argument. Right, we can have various pollutants in the atmosphere. Some are genuine pollutants. Like it used to be that, well, let's see, if we could talk to people that lived during the Industrial Revolution, where it first started in England, and all their energy was derived from coal, then you would find the city of London just blanketed with ash and smog. And certain cities in the US even today experience that smog. Los Angeles is a good example. But there are pollutants that are trapped in the atmosphere, and they're genuine pollutants. In other words, they're unhealthy for us. I'm not going to talk about global warming because it'll set me off. People that believe that carbon dioxide is the primary cause, man-produced carbon dioxide is the primary cause of global warming or global climate change, are off their rockers. There's no evidence for it. Okay. When we describe gases, we're gonna describe gases first physically, because if we understand how gases work from the physical standpoint, then we can use that information to help us answer questions in chemistry. Okay. So to describe the physical behavior of any gas, you need to know 4 variables, the values for 4 variables. You need to know pressure, volume, temperature, and the number of particles in the container. And I use this small n without the zero. With the zero, it's neutrons. But without the zero, n means moles, and moles of gas. So we need to know pressure, volume, temperature, and numbers of particles. How do you express pressure? Well, when coming out of the Dark Ages, modern science needed a way to quantify pressure of a gas. And the definition, we'll get to pressure, the inventions in just a minute. But pressure itself simply means a force per unit area. Okay, so remember, I hope I made this distinction between extensive properties and intensive properties. Did I do that? Extensive properties are those that describe some measurement that varies with the amount of something. So the force would be an extensive property. Say you have a kilogram mass and you lift it up. The force required to lift it is a certain amount in Earth's gravitational field. But if you have 2 kilograms, it takes more force. So the more stuff you have, the more force it takes. But if we apply that force over a given area and establish that value as pressure, then if we have that same value of pressure and you increase the area, then the force has to increase. So pressure is an intensive property. Doesn't matter how much you have, the pressure is going to either be constant or it's going to change with the ratio of force to area. Now, gas pressure can be described in terms of this force per unit area, or it can also be described actually with the earliest invention by Torricelli. Evangelista Torricelli was an Italian, obviously. And he invented this device called the barometer. I can't give you a lot of details about his inventive process, but he ended up with a pool, well, let's just use the animation, a pool of mercury. So you see the mercury's got that convex meniscus. That's what mercury does when it's in a glass container. And he used mercury. He had choices. He needed a liquid, right? Because he was going to use air pressure bearing down on the pool was going to be transferred, that pressure, into the column and give him a way to measure that air pressure on the pool. So he had choices, liquid choices, and probably the most obvious one would have been water. I don't know, he may have tried water and found that water wasn't dense enough, because 1 atmosphere pressure will cause a column of water to rise with a vacuum over it in the tube. Will cause the water to rise 33 feet. All right, so he'd need a glass tube 33 feet long. That wasn't practical. Now, the glass blowers of the day were very good at making tubes of uniform diameter. So he needed something that was denser. And the perfect candidate for that was mercury, because it's the only metal that's liquid at room temperature. Right? There's some that are close, like gallium. Right? If you put gallium in your hand, it'll melt, but it won't stay liquid at various temperatures. But mercury will. And mercury is very dense compared to water. So he found that his tube didn't have to be any higher than, say, 760 millimeters. So he took this tube and he filled it up with mercury, and he put his thumb over it, or his hand, and then he flipped it over and submerged it. Right? They didn't know about mercury poison back then. In fact, liquid mercury is not that dangerous. It's organic forms of mercury are deadly. I could tell you a story about that, but we may not have time. And then when he released his thumb and let the column of mercury go continuous through the tube and out into the pool, what he found was the mercury dropped, right? So that white area up there is actually the first vacuum. A vacuum, by definition, is if there's an enclosed space where there used to be matter and now there's no matter, that's a vacuum, right? So he created a vacuum there, and he found that if he put his barometer in the back of an ox cart and went up to a mountain, the mercury dropped, which was an indication of lower air pressure. And if we went from his location down to sea level, he found that the column of mercury went up. So he noticed a way to measure changes in air pressure. And this invention spread rapidly. Other scientists used it. They just take this barometer and just set it on the bench top and leave it there. And every so often they take another measurement and note atmospheric conditions. And they noticed that if it was starting to drop, poor weather was on the way. And if it went up, poor weather was gone and sunshine was back. So we still use that high pressure, low pressure differential to indicate whether we're expecting good weather or bad weather. Okay. There's predict the weather. Okay, I've talked over that already. Come on, there we go. So what we needed was a standard. Now you can take a barometer and set it at sea level, and the pressure will go up and down. So if we're going to say a certain height of that column above the pool level is, say, 1 atmosphere, we're trying to develop an equivalence. If we want to know what 1 atmosphere is, then scientists have to agree upon a standard, right? And the average height of that column over a long period of time for 1 atmosphere is 760 millimeters. Millimeters of mercury. So there we have one equivalence. And remember, whenever you have an equivalence, you've got a conversion factor. That's considered normal atmospheric pressure. So we could take If you're at a higher elevation, like we are here, we're about a half a mile high. You should expect on an average day that our pressure will be lower than it would be at sea level. And this is just an example. If you measure on a particular day that you have 694 millimeters of mercury, then what is that in atmospheres? Well, 694 millimeters of mercury is where we're at, and where we want to go is atmospheres. Right? This is dimensional analysis all over again. So we have millimeters of mercury in the denominator and atmospheres in the numerator, because that's where we're headed, and this is where we came from. So 1 atmosphere is 760. You just divide that in there, and you know you're going to get a value less than 1, which is, in this case, about 0.9 atmospheres. BKW is the FAA designation for our airport. I used to know a lady whose initials were BKW. If you go even higher, say go up another quarter mile high, then the pressure is going to drop some more. Right? So at Winter Place, you've got 669 millimeters of mercury, and do that calculation, and you should expect a much lower pressure in atmospheres. So we have 2 ways of measuring pressure. One is in atmospheres, one in millimeters of mercury. But those are not SI units. Those are not international standard units, right? This is, historically speaking, this is where we came from. These are the first available measurements. And in the beginning, we're going to focus on either atmospheres or millimeters of mercury, but I'm going to introduce you to the other units just so that the discussion will be complete. Here's another example. This is going to be greater than 760. Okay. The SI unit for pressure is the Pascal. 1 Pascal is equal to 1 Newton per square meter. So you'll notice if you use or study SI units for very long, there's an attempt with the SI system to make the units interchangeable as much as possible. And in order to do that, if we have 1 Pascal, then if we know that 1 Pascal is equal to 1 Newton of force per square meter, it makes it more amenable to unit conversions. But Newton is a derived unit also. Okay? And the Newton is based upon Newton's second law of motion. So he said the force that's applied to a mass will cause that acceleration. That's Newton's second law. So if we know that the mass is a kilogram and the acceleration is 1 meter per second squared, then the force that this represents is a kilogram meter per second squared. And that's equal to 1 Newton. Okay. So that allows us to do conversions if we have to break down a derived unit into smaller pieces so that we can cancel units. But that 1 Pascal is 1 Newton of force per square meter. And we have other conversions as well. So we have the Pascal is the SI standard. And then we have atmospheres, we have millimeters of mercury. We also have in the, rather than millimeters of mercury, we can convert that to inches of mercury, 29.92 inches of mercury. Okay. And all these are 1 atmosphere. Now that's not 1 atmosphere. It takes a certain number of pascals to make 1 atmosphere. We can use pounds per square inch, right? Pounds per square inch would be 14.69 PSI. So that's what what we use to measure tire pressure. There's another unit called the bar, and the bar is actually derived from the pascals. So 1 bar is equal to, let's see, how many? 1, 2, 3, 4, 5. 5, 10 to the 5th pascals. 100,000 pascals. And millibar is used on by weathermen or meteorologists. If you look at a detailed weather map, you're going to see these lines, you know, tracking around there, and you'll see back maybe a big L over here and a big H over here, and you'll see lines going around them, right? Those are isobars. That is, those lines follow in the atmosphere. Those follow the lines of equal pressure. So if you go from one to the next, it's supposed to be a certain number of millibars between the two. So weathermen use millibars. And I use men generically. There are weather ladies too. Now here's the equivalent to 1 atmosphere. 1 atmosphere is equal to 101,325 pascals. So what does that mean in terms of size of the unit? Remember, if the unit of measure, let's do it the other way. If the value in front of the unit of measure gets bigger, then the unit of measure has to be smaller. They run opposite one another. So the pascal is much, much smaller than an atmosphere. All right, we can convert to various, let me see, did I miss any? PSI, inches of mercury. We're going to convert that to atmospheres, inches of mercury, PSI to inches of mercury. And all of those conversion factors are derived from these equivalences. And if we can say this is equivalent to that, to that, to that, we could create a conversion factor with this and that. Right? We could say that ratio, if we needed it, we could say 14.69 PSI per 29.92 inches of mercury. If we wanted to convert from inches of mercury to PSI, that would be the conversion factor we'd use. And it's always based upon an equivalence. Okay. You just need to practice them is all. All right. This is something that I just put in for interest. You don't have to know how to do this. It's just how we would convert the pressure of a mercury column at 760 millimeters high with a 5 millimeter diameter tube, and do the calculations to determine the applied pressure in pascals. So that's 101.3 kilopascals. Okay. Kilopascals would be, move it 1, 2, 3 this way. So 101.325 kilopascals is 1 atmosphere. Okay, now that we've got an understanding for pressure, let's talk about a law that uses pressure and volume. Now that we have a way of measuring pressure, and alchemists already knew how to measure volume, we just needed an agreement upon what the standard of volume is, and we talked about that earlier with the SI unit derivation. So in 1662, Robert Boyle published his Boyle's Law. In Boyle's Law, takes two of these factors and holds the other two constant. For these first 3 or 4 laws, that's the way we have to do it. If we're going to let one vary with the other one, then the other two have to be constant. Okay, so Boyle's going to take these two and let them vary and see what happens, but these two must be constant. Okay, temperature and number of moles. So if he traps a gas inside a container, that will fix the number of moles. No problem there. Temperature, it depends. If your experiment happens over just a matter of minutes, temperature is not a problem. If you're concerned about temperature, just create an environment that is constant, like make an ice bath, right? As long as you've got solid ice and liquid water together, then you're going to have a constant 0 degrees. In fact, that's the standard temperature that we use for gases only. So standard temperature is 0 degrees C. Okay, Boyle said that with his experiments, he noticed that if he measured pressure and volume at the same time and did it over variable amounts of pressure, that he always came up with a constant value. Okay, so what that means is if pressure goes up, volume has to go down. In order for this to be constant, when that one goes up, this one goes down. And when that one goes down, this one goes up. Okay, that's Boyle's law. So we can put, this is just sample data. I think we just sort of made this up so it would illustrate the point. But if you do one experiment that says at 25 atmospheres, you have 4 liters trapped. So 4 times 25 is 100. Then if you change the pressure, and remember from our graphing exercise, what's the independent and what's the dependent variable? Independent is the one that I change as the experimenter. So Boyle changed the pressure. That's why the pressure is on the wrong axis. Pressure needs to be on the x-axis, and the volume is the response. It's the dependent variable. But you still get the same shape curve either way. And notice every time we change the pressure, we get an increase in volume, and the product is always the same value. And if we plot those values, we don't get a straight line. Right? We don't get a straight line. What we get, volume here. Let's be complete. This is atmospheres, and let's say this is in liters. We get a hyperbola. Does anybody remember what a hyperbola is from math class? Usually in math class, they approach it from a different angle. And a hyperbola, as I recall, actually has 2 parts to it. Right? You can graph it here, and it'll have a mirror over there. But from a physical standpoint, a hyperbola simply says that this curve will go out here to infinity, and will go up here to infinity, and never touch the axis, ever. Just think about it. If it did touch the axis, what would that mean? That would mean if it touched that axis, volume would be 0. And if you stuck a 0 in there, your relationship's gone. It doesn't work anymore. So it never touches the axis. That's a hyperbola in physical terms. Okay. So I don't know if I said it before, but scientists don't like curves. We can get a straight line, or if we can modify or transform data to give us a straight line, we're going to do it. The straight lines are better behaved than curves. There are some times when you can't get away from a curve, such as titrating an acid and a base. You get a sigmoid curve. There's no way to straighten that one out. So this relationship if the product of two variables equals a constant, it's always inverse proportion. The next one I'm going to show you is a direct proportion. As soon as we get through with Boyle's. So this isn't very useful unless you run the experiment and find out what the K is. Then you can solve problems under those limited circumstances. But the other thing that you can do is you'll notice that if you measure this at one place and get a volume at one place, that's equal to a constant. And if you change the pressure and get another volume, that's equal to that constant also. Right? In our example, that was 100. And we had an example here that equals 100, and then there's equal 100. Well, what's that mathematics law? I want to say it's not commutative property, it's something else. If A equals B and B equals C, then A equals C. So in this case, that equals that. So if you have an initial condition for volume and pressure, and you don't change the temperature or the moles, and you just change one of these values, then you're going to get a final condition. So you have an equation, and if you know the initial conditions, and you change one to get one of these, now you've got an equation in one unknown, right? Any equation in one unknown can be solved. So this is what I call before and after. This is a before and after problem. You still got the confined gas, and all you did was change one of the factors. That's one way to solve gas problems, if you know before and after conditions. And if you're looking at a word problem that gives you two pressures and one volume, suspect that you can use a before and after approach. So for instance, if we have a final volume of a gas, well, we want to know the final volume of the gas. So this is our unknown. If the gas is at 500 millimeters of mercury, starts at 500 millimeters of mercury, and at a volume of 15 liters, then what would, we change the pressure to 125 millimeters, what would be this volume? So now we have, that's a value, that's a value, that's a value, there's our unknown. So we could solve it and just say PI VI over PF. Right, I just moved this one here over to the denominator. We can put the values in as 500 millimeters over 125 millimeters and 15 liters here, like that. So notice we didn't have to change the values to atmospheres because this is a ratio and those units are going to cancel. So we still get the right ratio. So 125 into 500 times 15 should give us the new volume of our gas. And there it is, 60 liters. Now, does that make sense? That's the last question you should ask yourself. Does that make sense? Well, the pressure went from 500 and decreased. The pressure decreased, so the volume should increase. And it did. It went from 15 liters to 60 liters. That's an order of, that's a factor of 4, right? So is this a factor of 4? 4 times that? Yeah, that's 500. That makes sense. Okay. There's another problem we could do, but we use the same formula, only now we've got a different unknown. We want the final pressure, and we know the final volume from the initial volume and pressure. So we solve our equation for the unknown we want and then plug in the values. And as long as the units are compatible, right, we can cancel cubic feet, then we get our answer in PSI. All right, that was the first law. pressure and volume from Boyle's law. Then along comes a Frenchman by the name of Charles. That's his last name. So which one of these two did he hold constant? And why? Well, Charles wanted to say what happens to the volume when you change the temperature. So the temperature is the independent variable he's changing, and he's measuring volume as a response. This is constant, and this is constant. Okay. So how do you keep the pressure constant while you're keeping the number of moles constant? Well, the easiest way I can envision is a cylinder with a movable piston. Right? The piston is allowed to move, but you don't add any gas or subtract any gas. Whatever's trapped in there is there to stay. And then the pressure, you can keep the pressure constant by just adding a known mass on top of that piston, say a kilogram. Now you've got those fixed, and you can change the temperature and watch the volume. Okay, what did he discover? Charles discovered that the quotient of these two is equal to a constant. So as the temperature goes up, the volume has to go up. Right? That's the only way a quotient can be constant. So if this one goes up, that one goes up. So whenever you see two variables equal to a constant, and the variables are quotient relationship, that's a direct proportionality rather than an inverse like we saw before. And you can do the same thing with this one that we did with Boyle's law. Say this one's initial conditions, and this is final conditions. So V1 over T1 equals VI over TI equals VF over TF. And that's another before and after procedure. Now, the question may arise, why did Charles, well, actually, Charles did the work, and then Gay-Lussac used the results of his work, and back then they wrote letters to each other. They didn't always publish everything that they had discovered. And I suspect that Charles wrote letters to his friends and colleagues, and Gay-Lussac got wind of this relationship, and he used it in his work. And when he published his work, he gave Charles credit for this relationship. That's why we call it Charles' law, not because Charles published it. So why did it take so long, right? This is in a new century before we came up with this law. Pressure volume was in the 17th century, and we came into the 18th century to get volume temperature. We already knew how to handle volume. Temperature was the sticking point. We didn't know how to measure temperature reliably. We had various ways that we found we could measure temperature. Like I used to have one in my office before cats broke it. Was a Archimedes thermometer. You've seen it. It's a glass cylinder filled with a liquid, and you had these various glass bulbs in there with little hangers on them that gave you the temperature. And some of them would sink and the other would float because the density of the liquid would change with temperature. But that wasn't, I mean, you could get within maybe 5 or maybe 2 or 5 degrees, right? That wasn't useful. So what we needed was a reliable way to measure temperature, right? And that didn't come until the late 18th century. But here are the results that we can represent for Charles' law. In this case, we do have them in the correct relationship. Temperature is on the x-axis, volume's on the y-axis. So if we increase the temperature, right, we gradually get an increase in volume. And we can draw a straight line from that. Okay, so we have temperature here. This is in degrees C, and volume here, let's say it's in liters. And we have these points that we measure for a given gas. Now it'll change depending on the gas. Well, actually it won't. No, sorry, I misspoke. It should be the same for each gas. Well, okay. I'm painting myself into a corner. The gases will have a different line here, but they will all converge if we extrapolate. Right. Interpolation will be here. If we extrapolate down to volume 0, at what temperature would volume be 0? Now, we know that's not possible because atoms and molecules have a volume. But theoretically, the ideal gas would go down here, and this would be about minus 273 degrees C for all gases. So if you had one gas up here that had a different slope, right, it would end up at the same point, like that. So you could have different slopes out here, but eventually they'll come to this point. That was noticed by Lord Kelvin. And that's why his temperature system starts at 0. 0 K is absolute 0. The three systems of measuring temperature that are commonly used, Fahrenheit came first. Fahrenheit was, I think he was German. He was working with living systems. So his scale was based upon what were typically known as, well, his high temperature was body temperature, and he called it 100. Now we know for humans it's 98.6. But he took it as 100, and then 0 was the lowest temperature he could get. Ice and salt was 0 degrees, and then he just subdivided it. Celsius came along a little bit later, and he was a chemist. He wanted something that could be easily standardized, and it wasn't as variable as body temperature. So he took his 100 on the Celsius scale is boiling point of pure water at 1 atmosphere pressure at sea level. And 0 would be the freezing point of water. So he established his thermometer and subdivided it. Well, Kelvin used the same size units as Celsius, only he shifted the 0 point. 0 point for him is not here, it's down here. And I'll talk about that a little bit more later. But they needed a device that would absorb heat and respond in intrinsic fashion, because temperature, now we assume temperature is a measure of the average kinetic energy of all the particles in a substance. So when you measure temperature, if it's uniformly distributed, you measure temperature anywhere in the substance, it'll be the same. That's an intrinsic property. But they needed a glass tube, and they knew that liquids would expand as you heated them. But they needed something that was really stable and not volatile. Right? So water wasn't a good candidate, but mercury was. You can run the temperature of mercury up pretty high, and it won't be that volatile. It'll be slightly volatile, but if you confine it to a glass tube, then you've got nothing to worry about. So they designed the thermometer so that the measuring part of the thermometer was very thin wall glass, and then a thick outer with a capillary right down the middle into this pool of mercury. So the temperature transfer occurs down here and not much up here, because once you heat the mercury up and it starts to move, expands, then you want to be sure that the temperature throughout the column is roughly the same. So that's the device that was invented, and they they went from there. And measure the temperature of gases, liquids, solids, whatever the case may be. So there's where Kelvin's absolute zero comes from. Actually, it's a little more complicated than that. I've got a copy of his original paper. At the time Kelvin was working, thermodynamics was in its infancy. They were trying to figure out how to deal with what they called the heat engine. We still use the heat engine today, every day. I drove my car here using a heat engine. And they wanted to understand the physics of how these heat engines worked. It wasn't until Sadi Carnot, a Frenchman, proposed his solutions to various equations that we finally understood things about the heat engine, especially efficiency. Right. Sadi Carnot said that the efficiency of the heat engine is the high temperature minus the low temperature over the high temperature times the low temperature. That's a theoretical limit to the efficiency of a heat engine. So if you make the high temperature very high or the low temperature very low, then you get a better efficiency. Anyway, Kelvin was also interested, a lot of scientists were interested in this thermodynamic science that was developing. And he came to the conclusion that what they needed was a temperature scale that had no negative numbers in it. Because once you switch from positive to negative, that blows your calculations out of the water. So whenever we do calculations with temperature in them for gases, we have to convert the temperature to Kelvin. Otherwise, it won't work. Okay. I used 273. 273.16 is the more accurate version, but for our calculations, 273 works pretty well. Okay, and you can do the same thing with Charles' law before and after, like we did with Boyle's law, and solve for one unknown. All right. I'm not going to give you any equations that have two unknowns, unless it's an equation where you ratio. You want to know the ratio of two variables. Then you can treat that as one unknown. All right. I think there are one or two of those in our future. But most of the time, it's one unknown in your equation, and you know the values for the others, and you can solve for it. I think in algebra class, we did equations in two unknowns. And remember how to solve those? Anybody in algebra? You need two simultaneous equations, don't you? Right. That's the only way to solve a two unknown problem. But we're not going to do that. You can thank me with monetary gifts. Okay. So Charles' law, and I'm going to run out of time if I don't breeze through this one. Well, actually, we've got Thursday where I can finish up. So I just need to find a convenient break point. Let's see. How many pages? 6. I need to get through the third page. I do gas equation. Okay. I know where I can stop conveniently and then pick it up on Thursday. Okay, so we can solve these various equations, and notice that we had to convert Celsius to Kelvin in order to solve the equation. All right. Let's see. Now, I will add this. If you're given a problem in different units of measure, and you're going to solve a gas equation, you've got to get it in Kelvin. If you're given temperatures of Fahrenheit, then you've got to convert to Celsius before you can convert to Kelvin. So the equation, let's see, degree C plus 32. Your textbook and may say 1.8. 9 divided by 5 is 1.8. So either way it works. So there you can convert Fahrenheit to Celsius, and then Celsius to Kelvin. And Kelvin doesn't have a degree mark. Is degree C plus 273. There you go. And those equations should be in your useful information in the review document, which means they'll be on the exam too. Okay, next. After this, okay, we've done pressure, volume, we've done volume, temperature. Now we want to do volume, moles. And these are going to be constant. Actually, this is the Avogadro's law, is named after Avogadro, but he, like Charles, didn't publish it. I think other people published it and gave him credit. Avogadro's law. Avogadro said that if I control the number of moles, or the amount of gas that goes into the container, that's the independent variable, then the relationship is direct. If I put more, if I hold the pressure constant and the temperature constant, then the more moles I push into that container, the greater the volume. Okay. This is going to be extremely useful for us to solve stoichiometric problems. Because when you have a chemical reaction, if the reactants are, say, a total of 1 mole of this reactant, 1 mole of that reactant, but the total, and they're all gases, then the gases on the product side are actually a total of 4 moles. Then you've increased from 2 to 4, and you've also increased this from 2 to 4. That means the volume has to increase. All other things being equal. Okay. That's just where we're headed with it. And you can also set this up just like we did before. Final before and after problem. I wish I had time to talk about this. I only got 15 minutes. Let me see. Stop here. I'm gonna have to skip that discussion. The Karlsruhe Congress was a meeting of chemists from all over Europe, from universities and companies. They were having problems with their reactions because at that time they only understood mass and volumes. They would put masses or volumes together and have a reaction go, and then they usually would come out in a predictable manner. But when things went wrong, they couldn't fix it because they didn't understand that reactions don't occur as masses, particularly. They occur as individual particles, as atoms and molecules. And that the connection between that is attributed to Avogadro by his student, Cannizzaro. Let's see. So there's that example of stoichiometry I was mentioning. Another way to look at Avogadro's law is to say, if you have 2 containers, supposed to be the same volume. This volume is equal to that volume, and the temperatures are equal, and the pressures inside are equal. Then it must follow that the number of particles in each container are exactly the same. Okay. These are equal, that's equal, that's equal, this must be equal. So if there's a difference in mass between the two, that difference in mass must be due to the mass of the individual molecules or atoms. And that's how we relate numbers of things to masses originally, and then expanded by various methods from kernel of two different gases. Say we have hydrogen on this side and helium on this side. We know now that helium is average 4 atomic mass units per atom, and this would be each one of these would be 1, so that'd be 2. So the ratio of the masses would be, if all things are equal, the ratio of the masses would be something like 4 grams versus 2 grams. We would know this first, and we could infer that. Okay, notice here that we have 2 ammonias will decompose into 1 nitrogen and 3 hydrogens. So if we put a certain amount of ammonia gas into a container and allow it to decompose completely under the right conditions, then we would get actually 4 moles of gas as a product. So if we maintain the pressure and the temperature were, if it was isothermal, then the volume should double because we increased the number of moles by a factor of 2. So if we know that the initial volume was 35 cubic feet, then we should end up with 70 cubic feet. Okay, I got 10 more minutes. Let me see if I can get through this. Now, that's the way the laws were derived, by holding these 2 constant and let the other 2 vary. But in the real world, that rarely happens. Usually, all of them are varying at the same time. So what we want to do is find a way to combine those laws so that we can take advantage of them and solve real world problems. So the before and after problem would be to take Boyle's law is equal to final, and then superimpose on that Charles' law. Charles' law would be volume and temperature, right? So they need to be in a quotient relationship. Okay. And then if we put Avogadro in there, his is volume and moles in a quotient relationship. So there we have our combined gas law. PV over NT equals PV over NT. And we can let all of those vary as long as one of them is the only unknown. If we still have one unknown, we can solve it. And this is a animation of just what I put on the board. Okay. Now, one other thing we notice is that if each one of these in its relationship is equal to a constant, then this relationship here is also equal to a constant. Okay. That being the case, if we use certain standard units for each one of these, then we can standardize that value too. So if we say pressures in atmospheres, right? 1 atmosphere will have a certain volume if we have 1 mole of that gas, and we use a standard temperature of 273 K, which is 0 degrees Celsius. Then what would the volume be? Well, we measure the volume, and it's 22.4 liters. Okay? So if we do the math here, we get a value for K of 0.08206. Remember, everything you do to the numbers, you have to do to the units too. So it's liters times atmospheres divided by mole K. So with these conditions, that's our constant. So as long as we use atmospheres, liters, moles, and K as our temperature, then we can say this is going to be the constant. And we give that constant a special value. It's the ideal gas constant with those units. Now, there are other units of R, other values of R with different units, but this is the origin. So what does this help us do? Well, we've done before and after calculations already. What if you don't know the before? You only know the now, the state of the function. If you know that, and you use these units of measure, then you have pressure, volume, moles, and temperature. And if you solve this equation to make it linear, right, without all the quotient stuff, take this NT and put it over there. Then we have PV on this side, and we have NRT on that side. That's the ideal gas equation. And this will allow you to solve a problem that you don't know what the before was. You just know what the now is. Okay. I got 6 minutes. So that was derived from this combined equation. And now we want to talk about ideal gas. What do we mean by an ideal gas or a perfect gas? It stays a gas at all pressures and temperatures, no matter what the conditions. So we go all the way down to absolute zero and it stays a gas all the way down. That's the ideal gas. We know it's not real because you can condense gases into liquids. You can condense carbon dioxide into a solid, right? Dry ice. So we know that it's a theoretical situation. We also, and because of that, because we assume that it's a gas all the way down to absolute zero, it can't have a volume. That's why we say it's a point molecular volume. Remember in math class, when you were discussing dimensions, right? You have length, right? You have width, that's a single dimension. This would be 2 dimensions, right? Length and height. And then if you had width, that's a 3rd dimension. Well, a gas doesn't have any of those. We treat it as a point. A point has no dimensions, right? It has no volume. That's what we mean by point molecular volume. They don't interact with one another. When they smack into each other, it's just like billiard balls that bounce off. And of course, they have to obey all the gas laws. That's a given. Now, real gases do liquefy or some of them turn to solid as you decrease their temperature and increase the pressure. I think the coldest bulk that we can get is helium. Liquid helium is 4K. It's just 4 degrees above absolute zero. And it's really weird stuff. I've seen it in you know what a dewar is? It's like a thermos bottle, a big thermos bottle. It's got a vacuum in between 2 glass surfaces that are silvered to reflect the heat away from them. Okay, if you pour helium into that thing, it will climb the walls and out on the floor. It's the strangest thing I ever saw. They do actually have volumes. They do interact with one another. This is a real gas. They even interact with the walls of the container, right? They bounce off the walls of the container. If they didn't do that, we couldn't measure pressure of a gas in a container, right? It wouldn't strike our detector. Now, under what conditions can we treat a gas as ideal? Under low pressure, when there are fewer gas molecules, low pressure and small moles. Low P and low N go together. Okay. Low pressure and high temperature. The low pressure means there are very few collisions. There's lots of empty space. High temperature means that each molecule has a lot of kinetic energy. So when they do bounce off each other, and they have enough kinetic energy to overcome any interactions that's possible. And they don't stay together very long. So under what conditions can we do that? Well, low pressure is 1 atmosphere, just like it is here. Well, actually at sea level. But this is low pressure too, because it's less than 1 atmosphere. High temperature, compared to what? Compared to absolute zero. So 293 would be 20 degrees centigrade Celsius. So these are ideal conditions that we have right here. If you increase the pressure to 100 atmospheres and decrease the temperature to 25 K, then you don't have ideal conditions anymore. Okay, here's the ideal gas equation, and it was first proposed by Emil Clapeyron. You'll see his name again. There's the ideal gas equation. And these are the units. If you have liter atmospheres per mole K, that's the value. If we need to introduce the ideal gas constant into an equation that is energy bound, then we use a different one, 8.3145 joule per mole K. We'll use that one later. Okay. I'm about out of time. All right, we can arrange this equation in a host of different ways, just like any algebraic expression. That's nothing new. Or you can do this ratio. If we want to know the ratio of moles to volume, you can solve it like that. Okay. All right, let's see. Is this a good place to stop? I will remind you of this point. When we're talking about gases, if we say STP, that's standard temperature and pressure. If the problem is one of these physics type gas problems, the standard temperature is 0 degrees Celsius, which is 273 K. Standard pressure is always 1 atmosphere. That's going to be true for any of the gas problems that we work. Later on, when we talk about other chemical reactions, the standard is 25 degrees. But for gases, don't ask me why. The gases, our standard temperature is 0 degrees Celsius. Now they're saying low pressure. Oh, okay. What conditions prevail for one of the hazards of trying to teach from home is telephone. So ideal gases, the conditions for ideal gases are low pressure and high temperature. And conditions that we're experiencing right now, near 1 atmosphere pressure and room temperature, 293 would be room temperature, which is 20 degrees Celsius, would be considered both low pressure and high temperature. Okay, I think we talked about this one already. We derived the ideal gas equation. And for our purposes, initially, the R value that we're going to use equals 0.08206. And we have to be specific about the units of measure. Liter atmospheres per mole Okay. Later on, when we need the gas constant for working energy problems, where you need the joules term in there, then R becomes 8.3145 joules per mole K. But for now, the 0.08206 is the value we're going to be using. And I think we closed the last discussion with rearranging the ideal gas equation to give us these various possibilities. And it's simply an exercise in algebra, solving for an unknown. And we can solve for a ratio if we want. Okay. All right, now we'll pick it up with the sample problem. Calculate the pressure of a system with 2 moles of gas, 37 degrees Celsius, occupies a volume of 50 liters. All right. With any type of problem, word problem, I like to extract the information and put it on the board in a format that I understand. The number of moles is 2. And then we have temperature is 37 degrees C. We'll fix that in a minute. Volume is 50 liters. What do we have missing? What we have missing is the pressure. And that's what we want to, that's the question that needs to be answered. When you're presented with a problem cold, ask yourself with one of these gas problems, cold, ask yourself, is it a before and after or a state problem? And if it's a before and after, you're going to have 2 values for these terms, except for the one that's missing. And the one that's missing will only have 1 value. And that's your before and after situation. If you're only given values and you're not told what they were before, then you're talking about a state function and you need the equation like that. So we're solving for pressure. So pressure equals nRT over V. And remember, we have to change temperature to Kelvin because we can't have temperatures with negative values possible. That's why Kelvin works. Kelvin has no negative values. So this is going to be 273 plus that is 0 and 310, I believe. Yep, 310. So the pressure is going to be the number of moles. I might have to leave out the units because I don't have much board space. And then 0.08206. And the temperature is 310. That's K. And then the volume is 50 liters. Oops. There we go. And then if we do our math correctly, we should, and cancel units, we should end up with 1.018 atmospheres. So our system, given these conditions, will produce a pressure of 1.018 atmospheres. Second problem, we have a different set of data, and the unknown now is mole. Okay, so we have a temperature of minus 15 degrees C and 150 liters. volume, and a pressure of 850 millimeters of mercury. Okay, we're illustrating two problems here. One is the temperature is negative. We can't use it, of course. It has to be Kelvin. So what we would have to do is say 273 minus that value, which would be, let's see, 5 from 13 is 8, and 1 from 6 is 5, and it's 258. Okay. And the other problem is pressure. Our the value for R is liter atmospheres per mole K, which means the pressure must be in atmospheres. So how do you get atmospheres out of that? Divide by 760. Okay, so there's your temperature. And in this case, we use 2 decimal places extra. That's fine. It'll still work. All right, and there's your atmospheres. 1.118 atmospheres. Now we can solve our equation for the unknown, which is moles. Okay. And we just plug in the values. Once we have the correct units of measure, then we can just plug the values into the equation after rearranging it, making sure we cancel all the right terms, and we get 7.919 moles. Okay. All right. Now we're going to use what we've learned about gases to solve a stoichiometry problem. All right. Let's see. I need to be able to see myself. Keep it on screen. So this reaction is, let's name that compound, HGO. What would that be? Well, oxygen's -2. Mercury is one of those metals, right? So this is either a type 1 or 2. Mercury has the possibility for multiple charges. So it's a type 2 compound. We have to say what the mercury is. Well, a single mercury balances a -2 is a +2. So this would be mercury 2 oxide. Okay? All right. We don't need those right now. And then we have, this is a solid. And we got mercury liquid plus O2 gas. And we need 2 of these and 2 of those. So that's balanced. So what's the mass of mercury 2 oxide needed to produce 220 cubic centimeters? Right? Change that to liters. And we kindly did it for you. 220 cubic centimeters is 220 milliliters, which is 0.220 liters of oxygen at 25 degrees and 740 millimeters of mercury. And we're going to convert temperature to 298 K and millimeters of mercury to so many atmospheres. Okay. All right. So what's the mass of mercury needed to produce? Well, our gas equation gives us moles, not mass. But that's okay, because once we have moles, we can convert to mass. We know how to do that. Right? So there we get moles. Right? 8.755 times 10 to the -3 moles of oxygen. So how do we go from moles to mass? Molar mass. We need mercury and oxygen. Mercury is 259. 200.59 grams per mole, and oxygen is 16, right? Grams per mole. So now that we know now that we have 0. Let's see. Oh, excuse me. No, that's I'm jumping ahead of myself. We determined the moles of oxygen. Now we need the moles of mercury 2 oxide. So this is where we get the moles of mercury 2 oxide. And then we're going to stream these. This is a dimensional analysis problem. Moles of oxygen converted to moles of mercury 2 oxide, and then the mercury 2 oxide converted to grams. All right. So if we do our calculations correctly, we get 1.87 grams of mercury 2 oxide. Okay, that's the mass. Let's go back. 1.8693. Grams. So we found the moles here. Then we found the moles here. Then we found the mass here, which is this. Now we want to find out, since mercury is a liquid, we want to find out the volume of mercury. In order to do that, we have to know the density. So we're given the density 13.59 grams per cubic centimeter. Okay, so just divide that into that value, and that'll tell you there we go. 0.258 cubic centimeters of mercury, or 0.258 milliliters. It's the same thing. All right. So any balanced equation that has gases involved, we might find the ideal gas equation useful in our calculations for stoichiometry. All right. Now this is, I'm going to introduce, we're not going to fully flesh out the Dumas method because we're going to do a lab later on. I think it's the last lab in our series using the Dumas method. So when we get to that, we'll talk about it in much more detail. But this just introduces the concept of using what we know about gases and the gas laws to determine the molar mass of a gas. This person, Jean-Baptiste Andre Dumas, he's not the same one that wrote the Three Musketeers. It's a different Dumas. Worked with molar masses of gases. He did a bunch of other stuff too, but this is one method he is, which is attributed to him, in which he was able to, well, he did a bunch of other stuff, and they're listed there for you. I'm not going to read them off. This particular method allows us to determine the molar mass of any gas and we don't have to know the formula. Remember when we were doing calculations of empirical formula and yes, calculating empirical formula and molecular formulas. The transition from an empirical to molecular required that we know the molar mass of the compound. But we needed to get the molar mass without actually knowing the compound formula. If we knew the compound formula, we wouldn't have to go through all that mess of doing the empirical formula and making the ratios. So this is one of those methods for determining the molar mass of a compound without knowing what the compound formula is. It only works with volatile compounds, and by that we mean compounds that are easily converted, particularly liquids, from that state into a gaseous phase at reasonably low temperatures, anywhere from body temperature up to 100, 150 degrees Celsius. So when we conduct this experiment in the lab, we're going to use organic compounds that vaporize at temperatures below boiling point of water. Okay, once you get them in that state, then all you have to know is those four factors. Right? If you have a gas and you know the temperature of the gas in a container, you know the volume of the container, you know the pressure in that container, which in our case will be barometric pressure, then you can calculate the number of moles of gas in that container. If you know the number of moles of gas in that container, set that aside. We know the moles, and if you weigh the container before and weigh the container after, it contains now the gas. Then you can get that factor and you can calculate the molar mass of the gas. So that, in a nutshell, is how you do the Dumas method. As a practical matter, since we're going to be using the ideal gas equation and the formula for molar mass, we can combine the two. All right, this is something you do in algebra class, or you should do. If you don't do it, then you're going to learn it in this class, is combining equations so that we can do a single calculation once we have all the data. Right? So if we solve the molar mass equation for moles, and then substitute mass per molar mass in the ideal gas equation, and then reduce it and solve for molar mass, then all we need to know is the mass of the gas, gas constant, temperature, pressure, and volume, and we can answer the question, what's the molar mass of that compound? Okay, so here's a sample problem. Let me see if I got enough time to do this. I think I do. So if we have a 250 milliliter flask and it's got a lid on it with a pinhole in it, and the weight of the flask is 325 grams, we add a volatile substance, a liquid, place it in boiling water. So there's our temperature. And the atmospheric pressure is 710 millimeters of mercury. And we evaporate all the liquid inside the flask. And it comes Um, so we have our Erlenmeyer flask. We have a lid with a little pinhole in it. And we submerge it in boiling water. All right. And we have liquid in there. Once we vaporize all that liquid, and we put excess in there so that it will drive out all the air. So nothing is in there except the gas from the liquid, from the compound that we're investigating. Then once it gets filled with gas, right, then all we have to do is take this flask out and let it cool, and it will recondense the gas as a liquid. That's okay, because we didn't change the mass, we just changed its state. We know the mass of the container, which is 325 grams, and we put it on the balance again. We find out the difference is the new mass is 326.43 grams. So what's the mass of the liquid inside? 326.43 minus the mass of the container. 2546, I think. Yeah. So what is that? That's 4 there. This is 5. This is 7. That's 1. And this is 1. So that's the mass of the gas that was in the flask when we vaporized it. Okay, so we got the mass. Now we need to find out, get the other factors involved. 710 millimeters of mercury is 0.9342 atmospheres. That's good. 99.7 degrees Celsius is 372.86 K. And now I think we have enough information. Yeah. There's the mass of the vapor. Checking my math. Substituting these values in that equation. There we go. We know the pressure, we know the volume, we know the mass, R is a constant, we know the temperature. Now we can solve it for our molar mass. Just plug all the values in there. Be sure all our units cancel. All right, liters cancel. I'm going to have to fix this slide. Liters is supposed to be capitalized. It's not small l. That's an error. Let's see. Temperature, that cancels. And we're left with grams per mole. The only thing left over that's not canceled is grams and moles. And we find that our compound is 152.98 grams per mole. This is the Dumas method. All right. Consider the problem of calculating the final volume of some gas when 50 liters of gas at 250 degrees and 750 millimeters of mercury is cooled to 25 degrees and compressed to 900 milliliters. Okay, what type of problem is this? Is it a state function or is it a before and after? You're given 2 values for temperature, you're given 2 values for pressure, you're given 1 value for volume, and we want to know the final volume. So this is a before and after situation. I find it easier to start from the combined gas law. So Pi Vi over Ni Ti, yeah, equals Pf final, volume final, moles final, and temperature final. Start with this, and then look at your problem and say which ones changed and which ones didn't change. Right? Temperature changed. We're going to keep temperature. Volume changed. Pressure changed. The gas is confined, so we're not adding, and there's no chemical reaction, so we're not changing the moles. That means we don't need moles. They're going to cancel out anyway. So now we solve for final volume. This one. So we bring this one over here, that one over here, and final volume equals Pi Vi Tf over, let's see, yeah, Pf Vf Ti. Okay, so let's see, we have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Let's see, I messed up here. There. Okay, so this is the equation that we're going to be using. We just have to convert. Well, temperature is the only one that needs conversion, right? Temperature has to be in Kelvin, but pressure doesn't have to change because it's going to be in the same units. That means the ratio is the same whether it's in millimeters of mercury or atmospheres. And then the volume is in liters. Right? So that's the answer we're going to get is in liters. Units cancel here, units cancel there. So we get a final volume of liters. So here we're going to set up our problem. We're going to rearrange it. We're going to remove the moles because the moles didn't change. Right? So they cancel out. Millimeters of mercury cancel. Temperature was changed correctly. And so our final volume is 23.75 liters. Now, question is, does that make sense? Right? We started off with 50 liters, and now we've got 23 liters. Well, what happened to the temperature? The temperature got colder. So we should expect, as the temperature drops, the volume should drop. And the pressure increased. So the pressure-volume relationship is inverse. So if the pressure increases, the volume should decrease. Well, the volume decreased for two reasons. Temperature decreased and pressure increased. So yeah, it makes sense. All right. Okay. Let's see. I've already used up a half hour. Maybe I better pick up the pace. So here we have an equation where ammonia is decomposing into nitrogen and hydrogen gas. And this is a balanced equation. So if we want to calculate the final pressure of a system when 25 cubic feet of ammonia at 400 millimeters of mercury and 25 degrees Celsius is rapidly heated to 500 degrees Celsius and the vessel expands to 30 cubic feet, the final pressure. So in this case, notice that we do have a change in moles, right? Because this is a chemical reaction. We're starting off, our initial conditions means we have 2 moles, and our final condition means we have 4 moles. So we have to set our problem up so that we retain the number of moles. We have changed the moles. All right, so we set it up again, and we solve for the final pressure, and we can't cancel the moles this time. Well, we can cancel units, but we can't throw away the variables. So now you can keep the millimeters of mercury as is. We got the temperature correctly, 2 moles of gas, and this is initial, final is 4 moles. Temperatures cancel, cubic feet will cancel, so we don't have to change that volume. And then we solve this equation for millimeters of mercury. So the pressure is going to be 1,700 millimeters of mercury after the reaction occurs. It went from 400 millimeters to 1,700 millimeters. And multiple factors are involved in determining that value. One is the volume increased, so that means the pressure should decrease slightly, but the temperature increased almost double, so that would increase the volume. And we increased the number of moles. So Avogadro is telling us that the volume should also increase because we increased the moles. And in fact, we do get a substantial increase in pressure. Let's see. Yeah, increase the number of moles, we increase the pressure also. Okay. So that's a stoichiometry related problem. Okay. Next, we're going to look at Dalton's law of partial pressures. Let's fix that. Dalton's law of partial pressures. All it says, and this is John Dalton, the same one who proposed the atomic theory, is that when you have a total pressure measured for a mixture of gases, the total pressure is the arithmetic sum of the pressures that are attributed to each one of the gases in the mixture. So each one of those gases is exerting its pressure, and the total pressure is just a mathematical combination. However many. Okay? Now, what we're trying to explain in this equation is that if we solve the universal Cass equation for pressure, like that, then each one of those gases that is represented by these pressures can be represented by its own ideal gas equation. So what we're saying is that we can say the total moles times gas constant times temperature divided by volume is equal to the contribution of each one of these individual gases, which in itself can also be factored out as N1 for the number of moles for this one. R is the same, temperature's the same, volume's the same. So the only difference that produces the different pressures is the number of moles. Right? Everything else is the same. So we can factor out the RT divided by V. There we go. So we factor out the RT divided by V, and that's times N1 plus N2 plus N3. So if we set that equal to the original, N total times RT over V, these factors are the same. These variables are exactly the same. So they cancel. And that leaves us with the total number of moles equals the sum of the moles of one gas plus two gas plus three gas. Now, there's another unit of measure that's extremely useful in these expressions. So what we've determined so far is the number of moles total equals N1 plus N2 all the way up to N sub N. Okay. This unit of measure is called the mole fraction, and that's what it is. It's a fractional representation of each of the gases in terms of its composition in the total. So the mole fraction of N would be, of N1, would be moles of N1 divided by the total moles. Simple. So it's going to be a fraction less than 1. And if you add up all the mole fractions, the sum of the mole fractions equals 1. Unless you have not accounted for all the gases, then it has to be 1 within experimental error. So we can calculate the mole fraction for each one and add them all up. They have to equal 1. So each one of these, the individual pressures are equal to the mole fraction times P total. Why? Because P total, let's say, we'll use this as an example. P total is equal to the pressure of 1 plus the pressure of 2 plus the pressure of 3. And if the pressure of 1, if the moles of 1 divided by the total moles is equal to its mole fraction, and the moles are proportional to the pressure for each one, then we can substitute this mole fraction of 1 equals N1 divided by N total, which is equivalent to the pressure of 1 divided by the pressure of total. That makes investigating gases much simpler, right? Measuring pressure is easier than measuring moles. So if we measure the pressure of 1 and the pressure total, then that's the mole fraction. All right. Now, consider this as a practical example. This equation is the balanced equation for the rapid decomposition of nitroglycerin. So C3H5N3O9 is nitroglycerin. And its explosive power comes from the fact that 4 moles of nitroglycerin rapidly decomposes and produces 12 plus 10 plus 6 plus 1, which is 29 moles of gas. It goes from 4 to 29, and we know with that rapid increase in the number of moles, we get a corresponding increase in pressure. That's the explosive force of nitroglycerin. Okay, so if we take, we want to know the final pressure of nitroglycerin contained in a 100-liter vessel at 25 degrees and 20 millimeters of mercury. If we detonate it, and it's very sensitive, shock sensitive. So all we have to do is just, I don't know, tap the container. Or we could have a little spark inside and just hit that and it would decompose. And the vessel expands to 120 liters, 110 liters, with a temperature increase to 400 degrees. So there we have another force that's involved. If we change the temperature from 25 degrees to 400 degrees, we're going to get a rapid increase in volume. And if the volume is confined, our our combined gas law tells us that instead of volume, we're going to get pressure. So this is a before and after situation, and the moles of gas that changed from 4, right? The moles initial equals 4 moles, and the final moles equals 29. Okay. So we set up the equation and we substitute values for initials and finals, right? And the only one we have to deal with, convert, is temperature. The rest of them are moles, liters, and millimeters of mercury. Let's see. We want to know the final pressure. Okay. So everything's going to cancel except for millimeters of mercury. And we find now that the pressure is 297.61. So what was the initial pressure? 20 millimeters of mercury. So that container had to be partially evacuated. And now the pressure inside has, it's almost, well, let's see, 20 into 300 would be 15 times. We get almost 15 times pressure increase in this experiment. All right. Now let's take another look, a different look at this equation. If we have the balanced equation, then we know the relative amounts of each one of the gases, because all the products are gases, and the original is a gas. So what's the partial pressure of carbon dioxide, water, nitrogen, and oxygen in that final vessel? Well, we know the total pressure, right? What was the total pressure? Let's go look. 297.61. So the total pressure is 297.61 millimeters of mercury. Okay. So I'm thinking in terms of mole fraction gives us the pressure. Mole fraction times the total pressure will give us the pressure of each individual gas. So we take 12 divided by 29, we take 10 divided by 29, we take 6 divided by 29, and 1 divided by 29, gives us the mole fraction of each one of the gases in the as products in that container. Okay, so there's the carbon dioxide pressure, because we know that the mole fraction is 12 divided by 29 times the total. So that's the final pressure of carbon dioxide, the partial pressure of CO2. There's the partial pressure of water using a similar calculation, nitrogen and oxygen. And if we add those all up, they should be close to 297.61. Within experimental error. Okay? Some rounding error, I think, is involved there. All right. So the next topic we're going to investigate is the kinetic molecular theory of gases. Remember, up till now, we've talked about laws, right? Boyle's law, Charles' law, Avogadro's law, Dalton's law of partial pressures. Now we're going to try to explain why these laws work. Kinetic molecular theory. Now, this theory was proposed for gases first, but we found it to be so useful in explaining gas behavior that it was modified slightly and is now applied to all other materials, all other phases, liquids, and solids as well. Okay? It's very simple. Here are the basic postulates, that is, the conditions, the requirements for the theory to work. You need a large number of particles called atoms or molecules, right? We know that already. The particle size has to be very small compared to the distance between the particles. And remember, we're still talking about gases. So this is true. There's a lot of empty space in a gas. The gas particles are in rapid motion. That is, they have very high kinetic energy. And they're going to collide. And when they collide, they don't just collide with each other, they collide with the walls of the container. That allows us to measure pressure. And for the theory to work effectively, we can measure the temperature, and the temperature is an expression of the average kinetic energy of all the molecules in the gas. Now we know, in fact, when this theory was proposed, it was known that gases have a distribution of kinetic energies for their particles. But remember when I talked earlier in this discussion, we can't determine the kinetic energy of every particle and follow its progress through all its collisions. So we take an average value that is represented by the temperature. And we also have to assume that these particles, when they collide, they behave as billiard balls. In other words, they don't interact with one another. And this is under ideal conditions, of course. All right. So what's the outcome? Well, we're going to use an example here to describe what we mean when we say average kinetic energy. We're not actually talking about an arithmetic average where you take 2 plus 3 plus 5 plus 4 plus 1 and total them up and add them by the numbers and get an average. We need a different expression that will produce the expected outcome for the measurement of that temperature. So we're going to start with 7 balls, each weighing 5 kilograms. That sounds to me like maybe a small bowling ball. And we can calculate the kinetic energy of each one of those. If we know the velocity, we know its mass is 5 kilograms, and we know the velocity is each one of these, 10, 20, 30, 40, through 70 meters per second. We can plug them into the equation, and we calculate the kinetic energy of each one of these balls. Okay? Now, what's the average speed? We're going to do that one first. The average speed is simply 1 plus 20 plus 30 plus 40 plus 50 plus 60 plus 70 divided by 7. Okay, so if we do that, we get 40 meters per second. That's the arithmetic average of the velocity of each one of these balls. Okay, then we're going to calculate the speed based upon the average kinetic energy. Okay, if we calculate the average kinetic energy, we would take 250 plus 1,000 all the way down divided by 7. That would be the average kinetic energy that we would substitute in our equation. And since the mass of each ball is 5, then we could calculate the, after calculating the average kinetic energy, we could calculate the velocity that would be required to give us the correct calculation of energy. Okay, so that's 5,000 joules. is the average kinetic energy. Okay, if we rearrange this equation and solve for volume and substitute the energy, 5,000 joules, and the mass, and the constant 2, and take the square root of it, we get a value of 44.72 meters per second. Notice the difference. If we simply do an arithmetic average, we get 40 meters per second. If we used 40 meters per second instead of 44.72, we would get the wrong average kinetic energy. And the average kinetic energy is our focus. That's what we want to determine. So, how do we compensate? How do we calculate the correct velocity that we need to calculate the correct kinetic energy? It's a procedure called the root mean square. Oh, okay. So I don't have a slide on that one, so I'm going to have to try to do it on the board. So if we have velocities of 10, 20, 30, 40, 50, 60, and 70, the root mean square means you start from the backside, square. So you square each value. That's 100, that's 400, 900, 1600, 2500, 3600, and 4900. See, this is the velocity. This is the velocity squared. All right, so we got the squared of the velocities. Now we take the mean of these values. All right, let me get my calculator. I'm pretty sure I'm going to go over, so same rule applies. If you have to go, then you can leave. So 100 and 400 and 900. I'm adding these all together. 2500, 3600, and 4900. So that sum is 1.400 times 10 to the fourth. Now I want to divide that by 1, 2, 3, 4, 5, 6, 7. Right? That would be the mean of the squares. So let's see, 7 divided into that. And this is 2.00 times 10 to the third. All right, so this is the mean of the squared velocities. And the last step is to take the root. In other words, the square root of that value. So the square root of the means of those values equals the square root of that one. And I just hit one key, if I can find it. Here it is. And this is 44.72 meters per second. Okay? That root mean square process gives you the correct velocity for calculating the average energy. Okay. Let's see, what's next? So we're going to take the what we've learned about this kinetic molecular theory and apply it to an energy particle, atom or molecule, it doesn't matter, and how we would treat that as an individual particle and have to, if we had the computing power, and we do for one particle, how would we determine the energy of that particle in this environment? Well, the equation, this one, that one right there, that's for one direction. right? If the direction is linear like that on our scale. But suppose it's angled like this and angled like that. Then on our scale, we have to account for 3 dimensions. It's moving in 1 dimension, 2nd dimension, the 3rd dimension. That's what we've done here. We've split it out. So with the mass of the particle and mu, this is a representation. This is a variable symbol for the velocity. The velocity on the x-axis, the y-axis, and the z-axis. If we could do that, then we could determine its energy in this relative frame, this physical frame that we've created. If we did that for a mole of particles, and we had the average, the root mean square average velocity here for all the particles, then we could apply this moles times that one, and this would be the kinetic energy of the everything in the container. Right, there's the root mean square velocity, and they're using mu instead of a v, just so you don't get confused. Now, we don't have time to go into the derivation of this particular formula, but so it's going to seem like we're making a jump, a leap of faith, right? The association of the root mean square velocity of gas particles in a gas, root mean square, can be calculated if we know temperature, right? That's obvious because temperature is a measure of kinetic energy. If we know the temperature, our gas constant, and we know the molar mass on average, the average molar mass of the gases, okay, then we can use this equation to calculate. If we know the root mean square velocity and we know the temperature, we can calculate the molar mass of the gas. Or if we know the temperature and the molar mass, we can calculate the root mean square velocity. Okay. Now, in this case, we're going to be using the energy version of the constant, the gas constant, 8.3145 joule per mole K. We have to do that because energy is involved in this calculation. All right. So let's do it for air. What's the root mean square velocity for air? Well, we need an average value for the molar mass of air. And we know roughly that air is 21% oxygen and 79% nitrogen, with some argon and some of the others. So we're taking liberties, and we're just going to work from those two primarily, oxygen and nitrogen. But if we take the average molar mass of gas at 29.02 grams per mole, and notice that we have to convert it to kilograms per mole. Why? Because of this gas constant, joules per mole K. Well, joules is derived from Newton's second law. It's force equals mass times acceleration. Mass times acceleration, excuse me. And joules is force over distance. So distance is in meters, force is in kilograms, and acceleration is in meters per second squared. So this is kilograms meters per second squared. So this is, let's see. Yeah. And this is going to be joules. So that's kilogram meter squared per second squared. The point I'm trying to make is we have to convert molar mass to kilograms per mole because of the gas constant. Joules is represented in SI units, which is kilograms, not grams. So if you don't make that conversion, you're going to be off by a factor of 1,000. Okay. Once we make that conversion, then we can substitute values in this equation. Right. There's our constant. There's our numerical constant. There's our gas constant. There's our temperature, and there's our molecular weight. And we find out that air molecules are, on average, moving at over 500 meters per second. Okay, put that in perspective. 500 meters per second is 1,155 miles per hour. So what's the speed of sound at sea level? Well, it's a little over 700 miles per hour. So these gas molecules are supersonic. Okay, do the same thing for helium. Now you've got a different molar mass that has to be converted to kilograms per mole. And substitute that in at the same temperature, and you find that the average velocity of helium must be faster. Right? It's over double the velocity. Oh, excuse me. All right. So I got 6 minutes left. Now we're going to sort of back up and study another law, Graham's law of effusion. Sometimes it's called Graham's law of diffusion. Effusion and diffusion are two different processes. They're based upon the same gas behavior, but diffusion is a movement of gas through a bulk, like from one place to another in a space, and there can be other gases there. Effusion is movement of gas molecules through a barrier, right? But they're both based upon the same kinetics of the gas. So let's compare two gases, A and B. They're at the same temperature, all right? And if we ratio their velocities, right? And velocity times time is equal to distance, right? Remember, velocity equals distance for a period of time. So V times T equals distance, okay? So over a set period of time, the velocity will take that gas a certain distance, okay? But the gases are probably different. So we know that the velocities, as we calculated from our previous equation, will be different, right? So helium will travel much, much faster than air, for instance. So over the same period of time, the helium should go farther. And if we substitute those equations in here and ratio them, then we rearrange them. Everything cancels except for molar mass. So now, if we can measure the distance that gas A moves over the same period of time that B moves, then we can, and we know the molar mass of A, now we have an equation and one unknown, and we can determine the molar mass of this other gas. So this is another way of determining the molar mass of a gas, and you don't even know what the molecular weight or the structure of the gas is. This is an independent way of determining the molecular weight or the molar mass of a gas. All right. So the distance that two gases travel with respect to each other is inversely proportional to the square root of their molecular weights. I know that's a mouthful. It just means that this gas, let's say A is lighter than B. So this gas is going to travel farther than B. And the ratio of the two is a square root of the ratio of the two represents that ratio of the distance they travel. Now, what would this look like as a practical matter? Well, one of the ways that we used to demonstrate that our fume hood was working is we would take concentrated hydrochloric acid, right? Concentrated, and we would take ammonia, concentrated ammonia in solution, and they both tend to fume. So we get fumes coming up here. Well, if you put them right next to each other, they're going to mix, and they produce ammonium chloride solid. Very fine particles, just like a fog. And if it's in the fume hood, which it should be, the draft from the fume hood is going to pick those up and they're going to move through the fume hood and out the exhaust. And you can see that movement. Well, hydrogen chloride gas is 36 grams per mole, and ammonia is only 17 grams per mole. So which one's going to move the greatest distance, right? If we put them separated, then where are they going to meet? Let's move this one over here like this. Let's say ammonia over here, like that. Okay? So it produces fumes, and it's going to start migrating. These are going to migrate that direction. This is going to migrate that direction. Where are they going to meet? Well, the one that's lighter has the lower molecular weight is going to move farther. So this one's going to move over here. They're not going to meet in the middle. They're going to meet over here somewhere. And that's where you're going to get the fog. Well, it's difficult to control that experiment if you just have beakers sitting in a fume hood. But, excuse me, if you plug those values into the equation, you can find the ratio of the distance ammonia travels to the distance the hydrogen chloride travels, and that's 1.46. So in other words, ammonia is going to move almost 50% farther than hydrogen chloride. All right. So if we do this in a tube, a glass tube, like this, and we put ammonia in one end, excuse me, we put ammonia in this end, put hydrogen chloride in this end, the ammonia is going to move farther, and we can calculate where they're going to meet. And this is a better approach to it because now it produces a very fine line where they actually meet. And we just calculated in this 150 centimeter tube, the ammonia is going to travel 89 centimeters and the hydrogen chloride is going to travel 61 centimeters. Okay? All right. Now, this is a problem where we're proposing in a 120 centimeter glass tube, we're going to put ammonia in one end and we're going to put X, some other gas in the other end. But we need to know that they're going to react. So X is going to be a halogen. Ammonia and halogens do react to form that solid. All right. So we find that the molar mass, if we determine that the smoke ring happens at 87.9 from the ammonia, then we can ratio the distances traveled, right? Ammonia travels this distance, the other one travels this distance, and we can calculate the molar mass for the unknown. There we go, 127 grams per mole. And if we have these to choose from, right, these hydrogen halides, then we find that hydrogen iodide is the one that fits that the best. All right. Okay. During World War II, if you remember your history, the US was in a race with Germany against Germany and Japan to develop the atomic bomb. Our government-sponsored program was called the Manhattan Project because it started in Manhattan, in New York, but it took a lot more resources than that, so it spread out over the country. One of the places that was instrumental in purifying uranium 238 from uranium 235, and this is the one that produces the bomb. We needed to purify it. One of the cities that was instrumental in doing the research for this particular purification, separation, was Oak Ridge, Tennessee. I lived there for a few years as a kid, and I saw the from outside. I saw the large facilities that were developed to research different methods of separating these isotopes. One of those, and it was no small project because U-235 is less than 1% of the total. One of the plants used Graham's law to separate these two, law of effusion. So what we find is that the ratio of the two velocities using this molecular weight ratio means that the U-235 in its hexafluoride form, they had to convert this to hexafluoride because it's the heat of vaporization was much lower than the metal. They had to convert it into the fluoride. So that's why it's UF6. And it has a different molar mass here than you would find for the two isotopes. The ratio between the two is only 1.0043. So if you allow the gas under pressure to filter through any material, well, the special material that was required, then it only enriches it by 0.43% each time. So it has stacks and stacks and stacks of these filters, and each time they travel through, you got an additional boost in purification in favor of U-235. Well, the problem was we didn't have any materials that could withstand the fluoride corrosion. Stainless steel wouldn't work. Fortunately, DuPont, shortly before the outbreak of World War II, DuPont chemists had come up with a material called Teflon, which was impervious to fluoride corrosion. So this particular plant and the scientist behind that was Roy Plunkett. This plant called K25 was built in Oak Ridge to take advantage of the differential rates of effusion of these isotopes through the filters. And most of the floor space in this plant is taken up by those filters. It's just stacks and stacks and stacks and stacks of them. Um, as a kid, my family wasn't that rich, so if we needed entertainment, we just hop in the car and drive around the plant. They had barbed wire fences around it. You couldn't go in, but they had an access road that ran around it, and at the allowed speeds, it would take you 15 or 20 minutes to drive around this thing. It was that big. It was a 44-acre footprint just for the building. And the guards had orders to shoot first and ask questions later. Now, if you want to know more about this, here's the website, k25virtualmuseum.org, and you can get lots of details about this particular plant. Now, this was not the only plant that was built in Oak Ridge to separate U-235 from U-238. There were two other methods that were being investigated, and we won't go into those because it's not relevant to our discussion. Okay. So here's a comparison of ideal gases versus real gases, and this is just there as a reminder of the difference between the two. Okay. Now, when we're investigating gases, if we were engineers and we'd be investigating gases at much lower temperatures and under high pressures, we would need a way to correct this formula to selectively compensate for gas interactions that would naturally occur at high pressures and low temperatures. So that correction was devised by a man's name was van der Waals. His last name was van der Waals. And he proposed, there's Johann Diederik. He proposed this correction, and his research made him a candidate and a winner of the 1910 Nobel Prize in Physics. So this is his equation. There's the P. This is the V, right? Use the V in here with, let's see, no, this is a correction for pressure. So this is the added correction for pressure, and this is the correction for volume. Okay? Equals nRT. Now, you don't have to know this. I just inserted this to let you know that there are ways around the ideal conditions. You can, chemists and chemical engineers can work with gases under non-ideal conditions if they have access to these variables. Okay? All right, that's it. Any questions? I'm only 10 minutes over. If there are no questions, then let's see, that takes care of introduction of gases. And next Tuesday, we'll review for the exam on Chapter 8 that will be due following Thursday. And we'll also go in the lab and do experiment waters of constitution and hydration. Be sure and review the video. Watch the video in Brightspace that addresses how to conduct the experiment and how to deal with the values you get from the experiment. And then if you have any questions, we'll talk about that under let's see. Well, it looks like we've got we've got that lab, and then lab number 4, Boyle's Law, we're going to do the following week. So coming up, your report on lab techniques is due next Tuesday, and we'll do that lab. And then that report is formal. So be sure and use the example lab report I gave you to help you navigate producing your first formal report. I assume that most people here have never written a formal report for chemistry. So the first one is going to be a challenge, and then it gets easier afterwards. Okay, no questions? All right. Well, we're done for the day then.